Hello and welcome to Cashmatics. In this lesson we're going to be introducing complex numbers, and if you thought maths was difficult enough with all the algebra, all the numbers and all the funny symbols and stuff, we've made it even more difficult now by choosing some or making up some imaginary numbers. Now at first you might get a bit confused with these and wonder what the point of them is, and that will all come later once we've learned how to handle them. But what they actually provide us with is a kind of a porthole, like a shortcut to what can be some quite complex calculations, and it also allows to solve problems which you can't really solve without these complex numbers. So make sure you're really focused and have an open mind about this, but what you really need to make sure is that you come with some basic tools. So you know how to use indices, you know how to use trigonometry, your algebra is up to speed, you know how to deal with surds, and you know how to rationalize denominators and things like that. So make sure all of that is up to date before you continue with the lesson, because if you don't have those basic skills, you're going to struggle to understand some of the things. So grab yourself some paper and a pen and we'll get started. Before we start talking about complex numbers, we'll talk about the numbers we're used to using. Now, in the past, people only dealt with positive numbers because they made sense. You could count how many of whatever you had in front of you using positive numbers, and that's all the numbers that people knew. So when negative numbers were first introduced, people had a hard time understanding how you could possibly use them. So they said, how can you have -3 of something? It doesn't make any sense. But using them over time, people learnt the benefits of them. Okay, so when it comes to money, for example, negative numbers can be used to signify how much money is owed, and a positive number is how much money you've got. So that's how negative numbers were used, and people slowly got used to them. And because we've grown up with them, we're just accustomed to them, and we know exactly what they mean. So we've got the regular number line, which looks like that, and it goes on, forever that way and forever that way. But let's imagine there was another way we could go with this number line, okay, and it was in that direction as well, okay, and this is the imaginary number line, okay. So what we have now are numbers which are made up of a real component and an imaginary component. So the real components are just the numbers as we're used to seeing them. Okay, 1, 2, 3, 4, -1, -2, -3, -4. But then we have an imaginary component. So what we say is we have a number called I. Okay, and in some cases people might call it J, and we say that is the square root of -1. Okay, so we imagine you could actually square root -1. Now, the maths you've learned up till now, you'll think, well, you can't do the square root of a negative number. So, and the reason for that is whenever you square a number, it's positive. Okay, so there's no way you can square root a negative number because it wouldn't be negative in the first place. But we imagine we can, and we call that I. And from that, we can say, well, using the normal, rules of surd. So, for example, if A was root 3, A squared would be 3. And in the same way, I squared would be -1. And one of the first things we need to learn how to do is how to deal with powers of this letter I, or this, the square root of -1. And the way I find it easiest to deal with is by using using even powers of I to help me work out whether the answer is going to be positive or negative, or whether it's going to be one, or whether it's going to be imaginary, or whether it's going to be real. Okay, so for example, what I mean is, let's say we had I to the power 20. Okay, now what I do is I write that as I squared to the power 10. So when I said you need to know your indices and all that, this is the kind of thing I was talking about. In fact, my I looks a little bit like a 2. Let me just write it like this. Okay, I squared. So I squared, as we've seen, is -1. So that's -1 to the power 10. Okay, and we know that any number to an even power, well, I hope you know this, is always going to be positive. So the answer here is 1. But let's say we had I to the power 26, for instance. Okay, I to the power 26 would be I squared to the power 13, and I squared is minus 1, so minus 1 to the power, minus 1 to the power 13. Now, any negative number to an odd power would be negative, so the answer there is minus 1. Let's say we had something like I to the power 13. Okay, now the way I'd split that up is I multiplied by I to the power 12, which is I multiplied by I squared to the power 6. So that which is I multiplied by minus 1 to the power 6. Now, because minus 1 to the power 6 is going to yield a positive number, it'll be a positive 1, the answer to this is I. So I to the power 13 is the same as I, but if I had I to the power 15, I'd say that is I times by I to the power 14, which is I multiplied by I squared, I squared to the power 7, which is I multiplied by minus 1 to the power 7. Now minus 1 to the power 7 is going to be negative, and this is just going to end up being minus I. Okay, so that's how you deal with powers of I. It's important we can do that, okay? And that's not going to come into play till a bit later. The main thing you need to remember is I squared is minus 1, okay? And I is the square root of minus 1. So what we're going to do first of all is we're going to look to see how we can simplify surds using I, okay? So square roots of negative numbers using I. Then we're going to look at how to add and subtract these numbers with I in them, and then how we can multiply them as well. And the reason why they're called complex numbers is they're called complex numbers is because they're made of a real part and an imaginary part. So for example, if I had a number over here, okay, it's a little bit like coordinates, okay? The coordinates of that point are 3, 2, okay? But using this real axis and this imaginary axis, we say this number is 3 plus 2i. Okay, so that's the real part, that's the imaginary part, and the whole thing is complex. Okay, a number just like 3 is just a real number. A number like I is an imaginary number, but if it's got a real component and imaginary component, then it's called a complex number. So make some notes if you need to, and we'll move on to adding and subtracting these complex numbers. And we're going to do the surds. So the first thing we're going to look at is surds. So let's just say we had the square root of 16. Okay, the square root of 16 is 4. Okay, if I had the square root of 12, that is 2 root 3. I'm hoping you can do this quite quickly. Okay, and the square root of 200 would be 10 root 2. Now let's say we had the square root of minus 16 instead. Now, just like with a normal surd, what you do is you split the number up. So you have a square factor and another factor. Okay, so I can say that is the same as the square root of 16 times minus 1. And that would be the same as the square root of 16 multiplied by the square root of minus 1. So this bit is 4, and this bit here is I. So the answer is 4i. Now similarly, the square root of minus 12, okay, let's write that again. The square root of minus 12 would be 2 root 3i, and the square root of 200 would equal 10 root 2i. So the way you simplify these square roots of negative numbers is exactly the same as you're doing with a normal surd, the only difference being you hook an I on the end. But just make sure when you are writing your I, you're careful about how you write it. Okay, this I is independent of this root 3. Okay, so what some people might do is write it like this. Okay, and that can get confusing. Okay, and you might confuse yourself. So just make sure when you're writing it, you write it completely separately, or I suppose you could even write it before. Okay, but it's not. I don't know. So not a lot of people do that, but that's entirely up to you. I mean, what I suggest is just if you put that in brackets, then it's clearly separate to the I. Okay, but it's entirely up to you. Just make sure whatever you're doing is absolutely clear. So that's the first thing, and you can go away and practice some of those. But if you can do surds, you'll be able to do this. It's just a case of hooking on an I on the end. Right, the next thing we're going to look at is adding and subtracting. So imagine I had 3 plus 4i, I'll put that in a bracket, add 5 minus 7i. And it is literally just like doing algebra. There's nothing complicated about it. All you're doing is collecting like terms. Okay, so 3 add the 5 makes 8, so that's your real component. 4i take away 7i is minus 3i. And I'm really not going to insult your intelligence by doing many more examples. I'll do one more, but it really is as simple as that. It's just like dealing with algebra. Okay, so let's just say I had 2 minus 3i, add 7 plus 4i, take away 2 minus 3i, like that. Imagine I had something like that. Just be careful of your signs. Okay, so 2 plus 7 is 9, 9 add minus 2 is 7. Okay, minus 3 add 4 is 1, 1 take away minus 3 is 4, so that would be 7 plus 4i. And it really is as easy as that. And that's it. That's how you add and subtract complex numbers when they're in this form. And multiplying is also fairly straightforward. Well, at least the first part of this is. Okay, so if I had something like 7 multiplied by 3 add 2i, it is literally just a case of expanding the brackets. That's all there is. Okay, so 21 plus 14i. Okay, I'm not even going to do another one of those because that's quite straightforward. But let's say we had something like this. We're going to put something in double brackets this time. Okay, so 2 plus 3i multiplied by 5 add 2i. Okay, so you'd expand this just like you would with normal algebra. Okay, so you do the 2 times the 5, that's 10. Then you do the 2 times the 2i, that would be 4i. You would do the 3i times the 5, which is 15i, and then you would do 2i times by 3i. Okay, so I'm going to put this separately because that's the one we need to be careful with. Okay, so this, we've got a 10 over here plus 19i. Now let's just consider this a bit more closely. Okay, you've got 2 times 3 multiplied by I multiplied by I. Okay, so this bit here makes 6, but this bit here is going to be I squared, which is minus 1. Okay, so the whole thing becomes minus 6. So this here would become minus 6, not a plus 6. So let's just get rid of this plus. That'd be a minus 6. And this is where people slip up. Okay, so this would be 4 plus 19i. Okay, so normally negative numbers cause issues. When it comes to students that are doing GCSE and even A level tend to just slip up when it comes to negative numbers. But now when you're dealing with complex numbers, you've got another thing to worry about as well. Okay, so things which look like they might be positive end up being negative, and vice versa. But it all depends on what you're multiplying. So if you're multiplying two real numbers, then the rules apply as normal. But if you're multiplying 2 imaginary numbers, then you've really got to think about it carefully. And with time you'll get used to it, but just to begin with, just make sure you're being vigilant and watching out. Okay, I'm just going to do one more of these. Okay, and I'll try to do this in fewer steps. Okay, so let's just do one more over here. So let's imagine we had 4 minus 3i and 5 plus 6i. Okay, so I'm going to try and be extra careful here. So 4 times 5 is 20. 4 times 6i is 24i. Minus 3i times 5 is minus 15i. Now you've got minus 3i and you've got 6i. Okay, negative times positive. Okay, normally gives you a negative number. Because you've got an I and an I, that's another negative, which means it'll end up being positive 18. Okay, because the I times the I gives me minus 1. Okay, and I've got a minus 18, so minus 18 times minus 1 is 18. Okay, so you've got 20 plus 18, which is 38, and you've got 24i, take away 15, which is 9i. Okay, so that would be 38 plus 9i. Now dividing, much like multiplying, is quite straightforward as well. So, if you had something like, 3i, sorry, let's make that real. 9 plus 15i over 3, for example. All you need to do is divide each component by 3, so that would be 3 plus 5i. Okay, so that's quite straightforward. If you had 4 minus 7i over 3, you could split that up into 4/3, take away 7i over 3, and that's fine. Okay, now if you were dividing, if you were dividing by a complex number, so with all of these we were dividing by real numbers. If you're dividing by a complex number or even an imaginary number, something slightly different happens. And what we've got to do is we've got to go back to looking at what we did with surds. Okay, so let me just explain what I mean by that. Okay, so if I had 2 over root 3 and I wanted to make the denominator real, it's not real, sorry, irrational. Not irrational, so what am I talking about? Rational. I would multiply top and bottom by root 3, and that would give me 2 root 3 over 3. Okay, so that's a simple surd. If I had something like 2 over let's say 6 add root 3, what I would do then is multiply the top and bottom by 6 minus root 3 over 6 minus root 3. Okay, and that would give me 2 multiplied by 6 take away root 3 all over. So this would give me, this is the difference of 2 squares, so it'd be 36 take away 3, so it'd be over 33. And I could simplify that, or just leave it, not simplify it, but I could open up the brackets if I wanted to, but I'm just going to leave it like that. Now, when it comes to complex numbers, we do something very similar. Now, if you had a complex number called, so let's call it Z. Now that's normally the letter people use for complex numbers, and let's say it's A plus BI. There's something which is called its conjugate, which is A take away BI, and it works in very much the same way as this does. Okay, so if you compare this to this, you'll see how it's synonymous with what we've got over here. So if I had something, if I multiplied these two together, so Z multiplied by the conjugate of Z, so this is called the conjugate of Z. Okay, and remember this symbol, the star symbol, so Z with an asterisk. Let's just write it out. I've got A plus BI multiplied by A minus BI. And what that gives me is A squared plus ABI, take away ABI, and then you've got a minus B and a plus B multiplied together. Okay, you've got an I and an I, so end up with B squared. Okay, so these two cancel each other out, and I end up with A squared plus B squared. So the result is A plus BI multiplied by A minus BI is equal to A squared plus B squared. And that's an important result. It's the sum of 2 squares. Now you will have seen the difference of 2 squares in algebra and how to write that down. So A squared minus B squared is A plus B times A minus B. But with complex numbers, what you can do is the sum of 2 squares. All right, and what makes it handy is if you want to make the denominator of a complex number real. Okay, so for example, if I had something like 5 plus 3i and I multiplied it by 5 minus 3i, what I'd end up with is the 5 times 5 is 25, and this would be 3 times 3, which is 9, and that would give me 34. So these two complex numbers multiplied together have given me a real number. Okay, not any pair of complex numbers will multiply to give you a real number. It has to be a conjugate pair. So what we'll look to do is we'll do some examples on how we can use this to divide by a complex number. So let's say we've got this fraction over here, and what I want to do is get rid of the complex number from the denominator. So I want to make it real. So what I do is multiply by its conjugate, which is 1 minus 3i over 1 minus 3i. And the result of that, I'm going to keep the top. I'm not going to bother multiplying the top out. I'm just going to keep it as it is. And the bottom, using the sum of 2 squares, becomes 1. So 1 times 1 is 1. 3 times 3 is 9. 1 and 9 is 10. So that becomes 10. And now I'm going to expand the top. I don't like to do too much in one go because it's just too much information to hold in my head. So let's expand the top now. So I've got 3 times 1, which is 3, minus 9i, minus 5i, and minus times minus is normally a plus, but because they're both imaginary, it'll be a minus 15. Okay, all over 10, and let's just put that together. So 3 take away 15 is minus 12, minus 9 take away 5 is minus 14i all over 10, and that simplifies to minus 6 minus 7i over 5, and normally these get split up. Okay, so minus 6/5 take away 7i over 5. Okay, I'll do one more example. So let's do 3 add 5i over 6 minus 8i. Okay, now I'm just going to take my time here so you have a chance at guessing what I'm going to multiply by. So have a quick think, and hopefully you've thought of this. So 6 plus 8i over 6 plus 8i. Now, what might be a good idea here is to pause the video and see what you get from this. Okay, so if you pause your video right now, have a go, and then play it and see if you get the same result as I got. Okay, so the top becomes 3 add 5i multiplied by 6 add 8i all over, now this will be 36 plus 64, which is 100. So let's just sort out the top. That'd be 18 plus 24i plus 30i, and this will be take away 40, and this will be 100. And let's simplify a bit more. 18 take away 40, what's that? Minus 22, and 24i plus 30i, that is 54i all over 100, which simplifies to minus 11 over 50 plus 27i over 50. So what we're going to do next is have a look at solving quadratics. Now you might be wondering, well, why am I solving quadratics? The thing is, in the past, all the quadratics you solved, so for example, if your quadratic looked like that, you knew there were two solutions. If your quadratic looked like that, that's meant to touch the axes, there's one repeated solution, and if it went like that, then there's no solutions. I'm talking about when the quadratic equals 0. So it equals 0 twice here, equals 0 once here, and it doesn't equal 0 here at all. But what we can do is we can actually use these complex numbers to find an imaginary solution or a complex solution to this equation, this type of equation. So let's just have a look at z squared plus 121 equals 0. Okay, if I try to solve that equation, okay, if I plotted y equals z squared plus 121, it would look something like that. So we know this doesn't equal 0. Okay, not with real numbers anyway. But with imaginary numbers, we can actually solve it. Okay, z squared would equal minus 121, which means z is equal to the square root of minus 121, which is minus 11. Sorry, which is 11i. Okay, so there I've got a solution to that equation. You can also use the quadratic formula to solve these quadratics as well. Okay, let's get rid of this. So let's say we had something like, let's have a look, z squared plus 2z plus 5 equals 0. Okay, you might notice I put a little line through my z's, that's so they don't get confused with 2's. Okay, if I wrote my 2's like that and wrote my z's like that, you'd get a bit muddled up. So I put a line through my z's to make it clear to me that it's a z. And z's come up a lot, so get into the habit of doing that. It will be helpful to you. Now I can't factorize this. Okay, I could do this by completing the square. So let's do it that way. Okay, let's do that'd be z plus 1 squared. So I'd have to take away 1 and add the 5. So that'd be add 4 equals 0. And what I get is z plus 1 squared equals minus 4. So if I square root it, that means z plus 1 would equal 2i, because the square root of minus 4 is 2i. So z would equal minus 1 plus 2i. Okay, there is one thing I missed out here. When you do a square root, you get a plus and minus here. Okay, just like when you normally do a square root, it'd be plus and minus 2i. If I use the quadratic formula instead, so remember that is z equals minus b plus or minus the square root of b squared minus 4ac over 2a. I would get z equals minus b, so minus 2, plus or minus the square root of b squared, so 2 squared, which is 4. Take away 4ac, so that would be take away 20, all over 2. So I'll get minus 2 plus or minus the square root of 16, or sorry, minus 16 over 2. So that would be minus 2 plus or minus 4i over 2, from which I get minus 1 plus or minus 2i. So I get exactly the same solution. Okay, I've got two roots. They both happen to be complex. Okay, and in fact, if one of them is complex, the other one will be complex as well. Okay, so the way these quadratics work is your solutions are they're both going to be real solutions. Okay, and if they're not both real, they'll both be complex solutions. Okay, and the complex solutions always come in conjugate pairs, and we'll talk about these conjugate pairs in the next lesson. And we'll look to see how we can use them to solve quartics and cubics as well. And with that in mind, in this next video, you are going to have to know something about the factor theorem and how to divide a polynomial by a factor, like, for example, a cubic by a linear term. Okay, so you might have a cubic and you might have to divide it by z plus 1. Okay, so if you haven't already learned how to do that, then please learn it. I will go over it quickly in the video next time, but knowing how to divide a polynomial would be very useful, and also read up on the factor theorem. Like I said, I am going to skim over it next lesson, but it would be helpful if you knew how to do that. But anyway, I hope you enjoyed that introduction into complex numbers, and I hope you are as intrigued by them as I was when I was learning about them. And they do melt your mind a little bit to begin with, but you soon get used to them, and I think if you persevere, you'll see how amazing they are when it comes to solving problems. Anyway, I'll stop now, and have a good day or evening or whatever it is, and goodbye for now.